Welcome to Directions in Machine Learning, Automated Machine Learning and Automating Algorithms. We are now halfway through our program of incredible speakers, and what a better way to celebrate than this milestone than by introducing Sami Koyejo, who is an assistant professor in the Department of Computer Science at the University of Illinois at Urbana-Champaign. His research interests are in developing the principle and practice of adaptive and robust machine learning. Additionally, he focuses on applications to neuroscience and biomedical imaging.
I found this on the web.
Sorry, Siri went off. That's the thing of doing it live. Applications to neuroscience and biomedical imaging. He completed his PhD in electrical engineering at the University of Texas at Austin, advised by Joydeep Ghosh, and completed a postdoctoral research at Stanford University with a focus on developing machine learning techniques for neuroimaging data. His postdoctoral research was primarily with Russell Poldrack and Pradeep Ravikumar. He has also been the recipient of several awards, including a Best Paper Award from the Conference on Uncertainty in Artificial Intelligence, so UAI, a Kavli Fellowship, an HKI Early Career Spotlight, and a Trainee Award from the Organization for Human Brain Mapping. He also serves on the board for the Black in AI organization. Just as a reminder for people who are new, Sami is around to answer clarifications in the chat via the Q&A window. And we are going to keep some of those questions and additional ones for the live Q&A at the end. And without further ado, let's watch the talk.
Thank you, Nicolo, for the kind introduction. It's my pleasure to speak with you today. Thank you to the AutoML group for putting this awesome talk series together and for the invitation. So today I'll be talking about automating ML performance metric selection. Again, my name is Sami Koyejo. So there are two main ideas I'd like to get across in my talk today. The first one is outlining metric selection. In cases where we can rely on human judgment, I'm going to propose the second main idea today, which is metric elicitation. I'm going to argue that it's a promising solution to the metric selection problem. Fortunately, it can be efficiently automated. And I'll outline applications to binary classification and the specific application to machine learning fairness. So to start off, I'm going to talk about metric selection, and I'm going to set up the problem with a cartoon example. So suppose you're interested in the problem of predicting or diagnosing Alzheimer's, say for risk scoring purposes or for retrospective studies in a hospital, or a variety of different reasons. So you can do this by collecting a bunch of data, maybe hiring an enterprising young scientist, and or an AutoML pipeline, and they'll build for you a machine learning model. So here I'm illustrating a cartoon of a neural network model. And once you're done, suppose you see that the accuracy of your model is a pretty good number, say 94.1%. Now, you might be satisfied with this performance, or you might want to look more deeply into what the model has done and maybe ask questions about whether this is a good model or not. So in particular, suppose you dig a little bit deeper and look at positive and negative predictions from this model. In this setting, we're going to assume that positive means healthy, negative means Alzheimer's as a prediction. And you might then be interested in looking at the false positive and false negative rates, which capture sort of conditional probabilities of predicting healthy when a patient has Alzheimer's or vice versa. Now, say you get 90% false positive rate and 5% false negative rate. Again, you can ask yourself the question, is this a good model? Have I done a good job constructing a good classifier? Suppose you at least want to explore a little bit more. And so you say build a nearest neighbor model. This model gets, say, 89.6% accuracy, but has quite different false positives and false negative rates, 50% and 1% respectively. Suppose you dig a little bit more and consider a support vector machine. Say this has 80% accuracy and false positive and false negative rates of 10% and 20%. So you've done all this work, and a question that you might ask yourself is, which model should you use? So I've constructed 3 models. I have 3 different accuracy numbers. In standard accuracy, the neural network seems to be the best. If I'm interested in minimizing false positives, the SVM model seems to be the best. I'm interested in minimizing false negatives. the nearest neighbor model seems to be the best. And hopefully this cartoon highlights this issue of how do I select which model to use, which is tied to how do I measure what my model is doing and whether it's a good model. So how do you measure the performance of a machine learning model? Of course, like all interesting problems, the answer is that it depends. So it depends on many things. In this talk, I'll argue that it depends on the relative cost and benefit of different kinds of errors. And we're going to spend some effort quantifying how to construct and define metrics based on this idea of relative cost benefit of different kinds of errors. And I'll argue and highlight that we're going to think of metrics as a quantitative description of these trade-offs. And a lot of our work is going to be going from judgment to a quantification that one can use both to construct machine learning models and to evaluate them. So slightly more formally, metric selection is the task of choosing an evaluation metric. Of course, this problem is quite challenging and is compounded by the fact that there are lots of different metrics out in the literature. So just looking, for instance, at scikit-learn, which is a popular machine learning package, have metrics for regression, there's a list, metrics for, say, multi-label ranking, metrics for clustering. These are different machine learning problems they might be interested in solving. For each of these problems, there's a variety of different ways of measuring what good performance might be. And so you end up with a large variety of metrics, again, with the task of choosing what metric to use. I'll argue again that metric selection is unavoidable in modern machine learning and specifically in modern AutoML. It affects all of what it means to build a machine learning model, the way we build machine learning models in modern times. In addition to the high importance of the usual suspects, your choice of model class, your choice of how you construct your computation, the data that you use to construct your model. Metric selection is, I think, a underappreciated but often quite high impact component of building machine learning pipelines. So the choice of metric affects which model or hyperparameters you choose when you construct your models. It affects which function classes you think are best. It affects the downstream performance of your model. Ideally, it affects how you train your model as well. And so metrics play a key role in how we construct and use machine learning models in modern times. So one observation, which is worth highlighting, is that metrics are not exchangeable. So here's an example from ranking and recommendation. So here's a paper in 2010. At this time, there was a lot of work on recommendation systems. There still is, but this time, primarily in research, we were thinking a lot about recommendation systems. And this was around the time of the Netflix Prize, and there was a lot of effort in building machine learning models that were good at ranking for recommendation purposes. Interestingly, the Netflix Prize chose to use RMSE as the metric for evaluating whether a machine learning model was good or not. And so there was a long line of work by smart researchers who spent a lot of effort trying to get very low RMSE. And retrospectively, of course, we know that we should have maybe had some caution about thinking about RMSE as the sort of end-all of what good metrics are. In particular, subsequent work has shown that you can construct a metric that's really good at optimizing RMSE, but is actually quite bad at optimizing standard, say, top-end ranking performance. So in particular, there are naive, simple algorithms that do quite badly on RMSE, but in fact can do quite well when it comes to top-end ranking. And if one argues, I think correctly, that your task in a recommendation system is to do a good job of ranking items for users, then you might argue that the metric of RMSE is not a good choice, and overloading on that metric leads to worse outcomes than if you had selected the right metric for the task. Another observation, maybe insight, is that metrics can actually be contradictory to each other. So you can have two metrics that both seem reasonable on their face, but actually lead to, if you like, completely opposite outcomes or decisions. So a great example of this reasonably recently is work in machine learning fairness. So I'm talking about now an article out of ProPublica in May 2016. So ProPublica analyzed an existing machine learning model that was used for sentencing decisions the task of the model was to try to predict risk of reoffense. Now, these scores were designed by Northpoint, who used a calibration metric as a way they evaluated whether the model did a good job or not in terms of fairness. However, ProPublica looked at false negative rates and false positive rates. These are sometimes called the EO metric, and found that black defendants were twice as likely to be incorrectly labeled as higher risk than white defendants. Conversely, white defendants labeled low risk were far more likely to end up being charged with new offenses than blacks, with comparably low COMPAS risk scores. So again, here's a setting where we have two stakeholders. They both construct metrics. They both evaluate the same problem. Both are well-meaning in terms of the goal that they want of sort of improving fairness in a certain algorithm. But at the end, you end up with an evaluation that leads to sort of conflicting outcomes in terms of the two metrics. And this is now well known in the machine learning fairness world, but as an example of the fact that metrics can in fact sometimes conflict with each other. To maybe highlight this point one more time with maybe a simple example, I'm going to show a simple simulation analysis. So here I'm going to generate data from a simple logistic model where the weights are a bit special. So the weights are tuned so that larger values of D1 leads to a more skewed probability model. So sort of much more likely to pick one of the classes versus the others. And the metric in this setting is a weighted metric. So it weights how accurate each class is and how important each class is in the final classification decision. And the key quantity here is D2. And larger values of D2 leads to high skew in the cost of making prediction errors for, say, class J. So we have this setting where we have a weight for how likely different classes are, a different weight in the metric for how expensive certain decisions or predictions are. And if you evaluate what happens as I change D1 and D2, you can evaluate what happens in terms of a performance ratio. So a performance ratio here is the ratio of the quality of the results. If I optimize a model that's tuned to the metric that I actually care about, this sort of weighted performance metric, or if I just optimize a model that's good at optimizing accuracy by itself. And you might already know that models that are good at optimizing accuracy are somewhat sensitive to the sort of underlying class distribution. And so if I construct the model in two different ways, what you'll see here is that you can have a performance ratio that's up to 5 times better performance for a well-tuned model, tuned to the metric, versus a generic model that's just good at optimizing accuracy. So again, this highlights the importance of selecting appropriate metrics and selecting metrics that are sort of well-tuned to the task, and using those metrics in the way that we construct and evaluate machine learning models. So next you might ask yourself, clearly this is an existing long-standing problem. Maybe we can ask how the experts solve these kind of problems. What you'll find is in academia, you most often just use whatever the standard metric is in, say, different application areas. So most of machine learning and classification uses accuracy, maybe top K accuracy in computer vision applications, F1 measures, say, information retrieval applications. In my experience, most industry applications often are a bit more careful in selecting metrics, at least the sort of the front end. So they might, say, do a bunch of user studies or hire a consultant or economist, A/B tests to try and figure out what evaluation metric or sort of model class best ties to what we actually care about as a business. Again, this highlights the fact that this is a challenging problem and really not well solved. So in settings where one can rely on a human quality judgment and a human decision maker, I'm going to describe a procedure called metric elicitation, which we think is a promising method for addressing this metric selection problem. And the underlying idea in metric elicitation is to convert the metric selection problem into a query problem where we're going to ask stakeholders to quantify the utility. So how good are certain models? And this quantification will then lead us into an understanding of the trade-offs and then lead us into a definition of the metrics. So in real settings, what this will look like, or this looks like, is that we take our data set and model classes, use this to quantify the set of measurements that we care about and we wish to trade off. And then the key piece here is constructing this elicitation procedure that interacts with an oracle, which can be an expert or a set of users. And based on the queries, gets preference feedback and tries to use it to nail down the best notion of evaluation, so what the metric should be. Now, one could try to solve this problem using value queries. So you could consider, for instance, asking the stakeholders, how good is a certain model? This is appealing potentially to do, but unfortunately it doesn't work. And the reason it doesn't work is that stakeholders, humans, are not good when asked to quantify value of different models. So giving a numerical score to a model is quite hard to do. However, many stakeholders are quite good when asked to do sort of pairwise preferences. So if I give you a pair of models and I ask you to tell me which model you prefer of the two, most stakeholders are sort of much more able to answer this question. And I'll give a little bit of detail in a couple of slides about how this might work in practice. The next thing we noticed when we started this work is that too many queries often result in fatigue. So this process of asking queries requires asking lots of questions. And questions can be fatiguing if you have lots of a long list of questions or comparisons that you need to ask. And so our goal is somewhat more nuanced. And our goal becomes to accurately elicit the metric using few queries. In our setting, we're using pairwise queries. So we want to elicit the metric using the fewest pairwise queries we can get away with. So I should mention that there is a related work in the literature. So there's work on preference elicitation in economics and psychology, which is, some of it is classic, and there's been a lot of study over the years. There's work in machine learning that's most closely related, is work on contextual bandits, in particular because we're thinking of pairwise comparisons, contextual dueling bandits. One thing to highlight here is that most of the work in the bandit literature is interested in the best decision or the best function, and not necessarily in characterizing the reward function. And in the metric elicitation world, what we really care about is getting the reward function right. The reward function here will be equivalent to the metric. And so there's a bit of a gap in that literature compared to what our goals are. I should also mention that there's work in reinforcement learning that thinks about inverse reinforcement learning, which involves interaction with the environment and with users. Again, a lot of that work is much more interested in the reinforcement learning problem in practice and finding good functions, and much less in finding or setting good reward functions. And one way, or one of the keywords to look for if you're interested in this problem, is transportable reward functions. So I'll switch gears now and talk about the first of our applications of this metric elicitation framework to the task of eliciting binary classification metrics. And I like this example because I think it's reasonably straightforward and I think can be described reasonably easily. So in binary classification, the statistics that we like to use to evaluate models can succinctly be described as the confusion matrix. So if you haven't seen the confusion matrix before, it's a way to quantify different kinds of errors that a model can make. So for instance, the true positives quantify how often the ground truth is 1 and the model predicts 1. The false positives quantify how often the ground truth is 0 and the model predicts 1. True negatives quantify how often the ground truth is 0 and the model predicts 0, and so forth. And so using these statistics, you can quantify how good a model is in a population sense, using either a data generative model or good estimates of this quite efficiently using real data. And what you'll find if you look in the literature is that most of the metric classes that we use in classification problems can be computed as nested functions of the confusion matrix statistics. And so we're going to use this structure to our advantage. We're going to construct methods for metric elicitation to take advantage of structure in the confusion matrix. I'll talk about this a little bit more later on, but I wish now to mention that even though the confusion matrix has 4 numbers, there are actually fewer degrees of freedom. And the reason is the confusion matrix elements can also be thought of as probabilities. In particular, if I sum over the columns, the sort of column of true positives and false negatives has to sum up to the probability of ones in the data, and false positives and true negatives have to sum up to the probabilities of 0 in the data. And so in fact, even though there are 4 numbers in the confusion matrix in the binary setting, if I fix the data generating model or the data set, there are actually really 2 degrees of freedom. And so the model is not sort of, the confusion matrix is much more restricted than you might imagine on its face. This will turn out to be important in a couple of slides. I mentioned earlier that there are lots of metrics used in practice. So you can imagine simple linear metrics, here written in terms of 4 numbers, but as I highlighted in the last slide, these 4 numbers really, you can rewrite the metric in terms of 2 numbers, and we'll use this in a second in our elicitation procedure. There are a variety of other metrics that are common in terms of ratios. You can think of precision and recall and measures that look like that. There are, of course, much more sophisticated metrics that are quite common. Things like F-measure, variations on weighted accuracy, Jacquard measure, metrics like this. One thing to highlight that's important, and they'll also be more important down the road, is that metrics as functions are invariant to various kinds of monotonic transformations. So in particular, if I scale the metric by an arbitrary positive value, the metric is still the same because it's still going to order models. The statistics still orders models in the same way. And so scaling, overall sort of global scaling doesn't affect the metric. Additionally, adding adding a constant to the metric doesn't change the metric either. So the ranking of models under a metric doesn't change if I scale or if I add constants to the metric. So I mentioned that we use the geometry of confusion matrix and statistics of what good classifiers are as a way to understand and build elicitation procedures. So I'll go into some detail about how this works. So the first thing that we try to understand is what happens if I, given a certain data set or data generating model, what happens if I look at all possible confusion matrices corresponding to that data set or data generating model. It turns out that this set can be relatively easily characterized. As I mentioned earlier, even though confusion matrices have 4 numbers, really only need 2 numbers to fully characterize it. And if I draw out this set, it turns out to have some interesting geometry. So first, this set turns out to be a nice convex compact set. If you're familiar with ROC curves, the top portion of this curve is equivalent to the ROC curve, or closely related to the ROC curve, achievable on this data set. And then you can imagine a classifier that intentionally makes the opposite of the correct decisions. And this plots out the sort of negative part, the lower part of this curve. And combined, you can show that this is a compact convex set, which characterizes all of the possible confusion matrix statistics given a certain data set or a data generating model. So the next thing that we observe is that a linear metric, we're going to stick with linear metrics for now and expand a little bit later, is that a linear metric which weighs, again, how much we quantify in this setting, say true positives versus true negatives, is equivalent to a linear function of the confusion matrix. And so the task of picking a good linear metric corresponds to maximizing or finding the right linear function that corresponds to what the oracle or the stakeholders are interested in with respect to this set of feasible confusion matrices. In particular, by exploiting the fact that linear metrics interact with this convex set, the task of finding a good model, which you can think of as, say, finding the ideal trade-off statistics, corresponds to optimizing a linear function subject to convex constraints. Again, this feasible convex set. What is nice about this is that these kinds of problems are well understood in the optimization literature. And in fact, we know that the optimal will be somewhere along the boundary and will correspond to some tangent point, of some point that's tangential to this feasible set somewhere. We don't know where this point is yet, and sort of where this point is tells us what the oracle metric is. So through this series of arguments, what I'm hoping to get across is that we can convert the problem of finding the right metric that corresponds to an oracle to the problem of searching along the boundary with all of these tangent curves and finding the right tangent curve that's closest to the oracle notion of trade-offs for a certain classification problem. And so this is the task that we're going to try to solve. A bit of a diversion, but I think important, is how do we actually ask queries to oracles, so to users or to experts or other stakeholders. So in most of the work that we're developing, we're exploiting recent work or existing work on ways that you can show classifier statistics to users, potentially even non-experts, and have them give you preferences or compare them and tell you their preferences. And so there's existing literature that we are using, which helps us in this task of showing pairs of classifier statistics to oracles or to users, to experts, and getting feedback on preferences. I should also mention that there's an alternative way to do this. If we don't want to show the statistics, we can instead convert these statistics into actual classifier decisions. So we can take samples and make predictions on sort of random samples, and we will then give the users or experts sets of predictions on different subsets of data and ask them for preferences in this setting. And this is equivalent to showing the statistics, and at least from a statistical point of view, this is equivalent to showing the statistics. This is still work in progress in terms of nailing down the best way to solve the comparison question for experts and other kinds of users. So now that we've shown how we do the comparisons, and we've also highlighted how we try to convert this problem from a sort of generic finding a good set of statistics problem into finding a good trade-off along the boundary of the feasible set, we can now put these ideas together. So specifically, the way that our algorithm works is the first step is that we reparameterize this boundary. You can think of this boundary as a curve, and so we can characterize this curve in terms of angles. And once you have this characterization, the elicitation task now becomes finding the maximum point along this curve, because this maximum point will directly tie back to the trade-offs, which will directly tie back to the choice of metric. And so now we need to solve this problem of find the maximum point of a curve where the only way we can access the curve is via pairwise comparison. So we can't ask value queries of how good a certain parameter is or how good a certain trade-off is, but we can ask pairwise preference queries. So we can ask, for instance, how good is statistic A versus statistic B, using the techniques that I highlighted in the last slide. And so this turns out to be very close to an existing well-understood problem in computer science. This is effectively a binary search problem. So to illustrate this with an example, suppose I at the beginning of this search, I can ask queries theta A versus theta B versus theta C versus theta D versus theta E, as shown on the right-hand side. And I get 4 preferences. So the oracle or the user says theta B is better than theta A, C better than D better than C, and E better than D. Once you have those results, immediately that tells you that the optimum or the max of this curve must be somewhere between theta C and theta E. And so then instead of searching over the full space, I can now restrict myself to searching over theta C through theta E using the same kind of sequence of pairwise comparisons. And so you might recognize this as a binary search algorithm. Instead of using values, we're using pairwise comparisons, but it's effectively a binary search problem. And once you're done, we can show some nice guarantees for this problem. In particular, you can show that binary search provably recovers the oracle's weighted metric. So we can actually pinpoint what the weights are that best correspond to the trade-off the oracle must be making. So in particular, in the basic linear setting, the weights, as I mentioned, you only really need 2 weights because of the restricted degrees of freedom. So we need some weight for false positives and some weight for false negatives. These weights are telling us how important or how expensive it is to make a false positive mistake versus making a false negative mistake. And by asking order log 1 over epsilon queries, we're guaranteed to be order epsilon accurate in terms of quantifying or nailing down A1 and A2. Some nice other things you can say in the setting, you can show that you can't do better unless you make much stronger assumptions. So this approach, using binary search, achieves the optimal elicitation rate. The analysis for this mostly boils down to showing equivalence to binary search and then just using guarantees that already exist for binary search. We can augment the algorithm a little bit compared to what I described. So we can add a bit of a safeguard in the algorithm and show that with small modifications, this algorithm is stable to system noise. So for instance, if the oracle sometimes gives incorrect predictions or incorrect comparisons and other kinds of noise, say finite sample noise that exists when constructing real algorithms. And so this algorithm with small modifications is actually quite stable to lots of things that could happen in the system. We've done a bunch of additional work on this. We've gone beyond linear binary classification to multi-class classification. We've also considered a variety of more complex metrics. I'll talk a bit about the fairness application, which is one example of a more complex metric. But we've also tackled a variety of other function classes for metrics that are more complex than the linear case. We've also done a bunch of evaluation. I'm showing here mostly simulated evaluation, just showing that the elicitation works. The green curve is the true metric. The blue dashed curve is the elicited metric. You might notice that the curves don't exactly overlap. Again, metrics are equivalent up to, at the very least, sort of scaling and additive differences. And that's mostly what is showing here. But in general, they're equivalent up to sort of arbitrary monotonic transformation. The red vertical and the black vertical lines are showing the true maximum, so the best model, and then comparing it to sort of the best model under the elicited metric, showing again that we generally have high quality results and do a pretty good job in nailing down the metrics that we're interested in. Now I'm going to switch gears from talking about binary classification to maybe more recent work that we've been doing, trying to understand the extent to which you can apply these kinds of ideas for problems in group fairness. So fairness is an extremely complicated topic, and I'm only going to sort of scratch the surface of the problem. And I'll cover background that I think is most relevant for the description and discussion I'm going to give today. So in group fairness settings, one of the ways that we try to quantify what fairness is to look for similar metrics across groups. So suppose we have, say, male-female or black and white groups or other kinds of group decompositions. We might say that an algorithm is fair or a machine learning model is fair if it has similar statistics across the set of groups that we're interested in, sometimes or often more than 2 groups. It's worth highlighting again, as I mentioned at the beginning, that it's hard to figure out, it can be hard in the abstract to figure out which metric to use in order to quantify or determine whether or not we have a fair model. So in particular, metrics can disagree in terms of what of quantifying potential fairness of a model class or a set of models. There's a bunch of existing work that has tried to quantify or determine the extent to which we have fairness in our predictive models, particularly in group fairness. So I would say the most popular approach is to look at accuracy, which you can think of as the sum of true positives and true negatives. And this is asking if accuracy is the same across different groups. There's also work on approaches like equality of opportunity, which looks at whether the true positives are equal across the different groups. And also statistical parity, which asks whether the true positive plus false positive, so the sum over the row, if you like, of the confusion matrix, the first row in this cartoon example, is the same across the different groups. And this is, again, a different definition of what it might mean for an algorithm to be fair. to again really highlight the point of sort of the breadth of metrics, it's again worth, I guess, loading or noting again that there are lots of different ways that we think are all very reasonable definitions of what it means for an algorithm to be fair. So I'm going to talk about some of our work in trying to come up with an algorithm for quantifying fairness using very similar approaches to what I described a few minutes ago. I should mention on the outset that in this work, we used rate statistics as opposed to the confusion matrices directly. So if I take my confusion matrix, if I column normalize it, so I divide each column by the sum of the elements in the column, I get the rates. So in this case, true positive rates and true negative rates for binary classification. But the same exact approach is also equivalently used for more complicated, say, multi-class classification problems. So again, just sum over the columns and normalize. And as I'll mention in a couple of slides, using rates instead of confusions directly ends up simplifying our problem and making it sort of more tractable. Similar algorithms will end up being useful. So given a classifier, the rates are given by, again, say these normalized statistics. And if I'm looking at these statistics across lots of different groups, then I can come up with a set of rates across all the groups. So if I have m groups, I just have a tuple of rates for each group, where each group is quantifying the statistics for that group. And in the second, we'll talk about the task of, again, trying to look for some kind of parity of these rates across groups as a definition of fairness. So in particular, we used the approach of fairness violation. So given two groups U and V, the fairness violation is quantifying how different the rates are for group U versus group V. With this definition, I can summarize our definition of fair classification metric. So this involves three terms. So the first term, which is the first function here, is the quantification of the utility. So this is akin to accuracy, telling us how good this rate statistics are purely in utility terms. The second term is the fairness term, which is capturing a weighted discrepancy. So the discrepancy, again, is this DUV term, which tells us how different the rates are. And then we have weights on these for every pair, which tells us the trade-offs between the different rates across the different groups. And then finally, we have this term lambda, which is a trade-off term, which is telling us in this setting how important is the utility term versus the fairness term. As mentioned, the metrics are invariant to various basic transformations. In our setting, the way that we quantify this is that we normalize the A's and B's to be norm 1. And so the task that we now are interested in solving is we're interested in finding the B values which quantify the trade-offs across groups. We're interested in quantifying the A values which quantify our utility, so how much we are valuing trade-offs across the different rates. And we're interested in quantifying lambda, which tells us the trade-off between the utility term and the fairness term. And so our elicitation problem is to elicit these three terms. So there are various challenges that we need to address in order to solve this problem. First, the overall rates and group rates are correlated, so joint elicitation can be somewhat difficult. In addition, we need to consider both positive and negative fairness violation. So we lose the sort of simple linear semantics that we had in the first example. In addition, the more groups we have, the more parameters we have. And as we'll show, the number of queries that we need roughly scales with the number of degrees of freedom, so the number of parameters that we need to elicit. The main things that we exploit in this problem is, just like in the confusion matrix case, it turns out that the rate statistics have a lot of interesting geometry. Again, the set of rate statistics is convex. Unlike confusion matrices, it turns out that the set of rate statistics also always intersect. So there always exists a point associated with a completely random classifier across all the different groups that has the same rates independent of different demographic groups, for instance. So there always exists some classifier that will have the same value in terms of race statistics, even if it has different confusion matrix statistics. And the reason is class prevalence. So group prevalence, sorry. So the fraction of your data points that come from different groups end up changing what the race statistics are. So because of this, we're able to always find some set of points that's feasible across all the different groups, and we'll exploit this in how we construct and solve the elicitation problem. Another nice thing is we understand quite well, again in geometry, the sort of corner points of this set. So we can easily characterize all of the points that are shared across all the different groups, and to a large extent characterize what the geometry looks like of rate statistics across groups. So our approach has three main steps. In the first step, we are going to elicit the misclassification cost. Second step, we're going to elicit the fairness violation. And the third step, we're going to elicit the trade-off between the two terms. So for eliciting the misclassification cost, our approach is we're going to exploit the fact that we know that these sets intersect. And in fact intersect if I give the same rate statistics to the oracle to compare across all the different groups. Say again, different demographic groups. So if I construct my queries in this way, it turns out that the discrepancy term is 0 because all groups have the same value. So the difference is always 0. And so the second term goes away. And so this problem turns out to be linear. And I can now apply methods that we already know how to solve for eliciting linear metrics in order to find the value for A. So in summary, by restricting ourselves to a certain set of possible kinds of queries, we can apply the tools that we have already developed for eliciting linear metrics as a subroutine for now eliciting this A value, which is the utility function value. The second part is to elicit the fairness violation. And to do this, again, we construct a special kind of set of queries and which exploit the geometry of the set of rate statistics across classifiers. To describe this, suppose we just have two groups. So in these two groups, I can construct queries that consist of both the statistic that I'm interested in and sort of a trivial statistic, which corresponds to a classifier that sort of always predicts a certain class for the second group. And if I do this, what you can show is that, again, the problem linearizes. And so I can solve this problem for, I can set group 1 and group 2, run this elicitation procedure, either evaluating for group 1 or evaluating for group 2. And skipping some of the details of the algebra, you end up with a system of equations that you can solve. And with more than two groups, you can solve this problem m times. So you have m choose 2 problems to solve. And once you're done, you're able to elicit the B value. So given the A, you're able to run a second elicitation procedure to evaluate the fairness violation. The third part is eliciting the trade-off. To do this, again, we exploit our knowledge of the geometry of the rate statistics. And with a bit of manipulation, you can show that if I select one group and then null for all the other groups, this problem turns out to have a lot of structure. In particular, maximizing over the rate statistics, which is something that we know how to do offline, ends up giving us a strictly quasi-concave function in terms of the trade-off term. And so I'm now able to set up a search procedure that searches for a trade-off term. If the problem is strictly quasi-concave, I can again use binary search like we used all the way at the beginning in our first algorithm. And so at the end of this, we now get the alpha term, which is the trade-off term. And so we can give some guarantees for this procedure. With k classes, I roughly need sort of k-squared queries to elicit the utility part of this. I need m choose 2 times k-squared queries to elicit the trade-off fairness parameters. And I need order 1 queries to elicit the trade-off term. The thing to highlight here is that the number of queries roughly scales with the degrees of freedom. We've, in subsequent and ongoing work, I've been looking at restrictions that have sort of fewer degrees of freedom, so restricting our fairness metrics to a smaller class, which has the positive benefit of maybe reducing the number of queries. But it's worth noting that the current methods that we develop roughly scale the number of queries, the complexity of the problem and number of queries based on number of parameters that we need to elicit. I'll very briefly talk about some empirical work where we try to compare how well elicited metrics work compared to, say, just doing default metrics. So we looked at a variety of standard fairness data sets. We constructed 100 classifiers of different function classes. And what we're interested in is asking how well does evaluation and ranking using the true metric work compared to, say, a metric that uses equal weights, so set lambda equals 0.5, and equal weights for all predictive terms, which is equivalent to just accuracy, and equal weights for all discrepancy terms. So set A and B to 1 and have lambda equals 0.5. So you can think about this as a sort of default or naive approach. And then we also compared this to a metric that only uses accuracy alone and completely ignores the fairness component. And what you find is the elicited metric works really well. It correctly ranks all the different models. So the best model is at the top. All the different models are underneath it. What I'm showing here on the left is evaluation of all of these methods using Kendall-Tal across all the different model classes to see how well it ranks the results, and also using NDCG. And the key takeaway is that elicitation works best and does better than naive or default methods for trying to compare different models. And hopefully the key takeaway for you is, one, it's important to, again, choose the right metric, in this case, the fairness metric for fair ML problems. And two, this elicitation approach can be quite effective in practice. So just to recap, I primarily covered two ideas in this talk. The first idea was metric selection, and I highlighted again that this is an important problem and one that shouldn't be ignored when constructing machine learning models. Second, I talked about metric elicitation. So in settings where we can rely on human judgment to tell us whether models are doing a good job or not, one promising way to help nail down how to compare different models is to use a metric elicitation procedure. Now, we've been working on this for a while, and we've made, we think, some good progress. We think that there are lots of extensions and open problems still yet to solve. So we're working, for instance, on extensions to ranking, regression, other kinds of machine learning problems that are richer than, say, the classification problem. We've been exploring a variety of query mechanisms, both in terms of different kinds of queries from pairwise preferences to maybe auctions, and also in terms of the HCI component. So how do we best ask users for comparisons or preferences? We've also been working on the robustness of these approaches, user population effects, combining results across multiple oracles, and noise tolerance. So I'll leave you again with a thought that metric selection is a required step in modern machine learning and AutoML in particular. And the key takeaway, hopefully, from this talk is that elicitation provides a way to automate the model selection. Thank you.
Great. Thank you for this talk. It was, I mean, mind-blowing. I really, really like this line of work. I think I spotted one of your papers, and I was hoping you would talk about this because its potential to really change the way people think about metrics is just staggering. I have a long list of questions. We have kind of 11 minutes left. I have a long list of questions, so I'm going to just go ahead and start. We won't probably get to all of them. People have asked, so by the way, thank you for all the people who asked a bunch of questions in the chat. And also thank you for responding to all of them. So one question, well, it seems more philosophical, but it's kind of interesting. How much is the choice of metric driven by requirements of differentiability in the community? I think this person is referring to just the general practice. And perhaps is also smoothness because of optimization, easier optimization.
Yeah, so that's a great question. It actually is. So it is driven by these choices, but in a somewhat subtle way. So when I say subtle, what I mean is the metrics we're referring to are the actual sort of final evaluation metrics, not necessarily the optimization metrics. And so, again, as I outlined, different fields pick various evaluation metrics, accuracy, F measure, things like that. These metrics are not differentiable. So accuracy is not differentiable directly with the class model we typically use. Neither is F measure. In classification problems, almost all the metrics we use require making hard decisions and then combinatorial sort of combinations at the end. So I guess to the point of whether it's differentiability, not directly. I would say that for many of the, say, simpler metrics, we can come up with surrogates fairly easily. And those surrogates are reasonably well behaved, so log loss, range loss, things like that. So I guess I want to say that may be a reason. However, the analyses sort of connecting the surrogates to the sort of true metric actually often happens later. So it's also not clear that it's a direct line. Yeah, so it's kind of mixed, but yeah, it's somewhat related.
Great, thank you. And then the next question, I think you must have gotten a lot, particularly by machine learning audiences who like black box function approximation. So somebody asked, have you thought about replacing the linear model in the first part of the talk with an arbitrary function approximator? I guess a neural network is implicit in the question, or is it an issue with sample complexity?
Roughly, yes. We thought about it, and it's a couple of things on sample complexity. So we thought about it. We haven't sort of formally written or published anything. We have thought about much more complex function classes. So many of the metrics are beyond linear. I only showed linear results because it's sort of the simplest case to discuss. But now we know how to do linear metrics, we know how to do ratio functions, which come up a lot. So F measure, Descartes, things like that. We know how to do quadratic metrics and various polynomials and sort of ratios of polynomials. In terms of generic sort of arbitrary function classes, our results so far suggest that the query complexity roughly scales with the degrees of freedom, which corresponds to sort of number of parameters that you need to elicit. So I suspect that will be true for if one uses a neural network model as your function class. The specific strategy for doing it, we're still working on. I don't think we have a method that we're really happy with for sort of general purpose function classes. Right now, our methods still use the properties of the function class in a sort of direct way. But I suspect then that you'll pay a really high query complexity to get good accuracy, and then I think you have to decide whether that trade-off is worth it. In terms of maybe sort of lower bias towards what the actual metric the oracle might be interested in, but at the cost of many more queries to get a good answer.
Right. Yeah, that's very interesting. I suspected it was like, yeah, you probably need so many queries. Although the queries are relatively cheap, right? Because if you have a trained set of models, which I assume maybe it's a part that takes time, then you just go back to the stakeholder and just ask to pairwise rank a bunch of things. So it's just human time, just.
Yes. Yeah. Okay. Exactly what you said. Yes, it's human time, but I think the just part that could be, yeah. Particularly if the oracles are experts and so may have limited appetite for really long query times. And our motivating applications, oracles are medical professionals, for instance. And so, yeah, it's hard to get huge stretches of time. So we're quite sensitive right now to thinking about query complexity.
That's, I guess, a nice segue into my next question, which is about extensions to multiple stakeholder settings. I'm sure you gotten this question a bunch, because you can imagine molecular tumor boards, stuff like that. You have multiple stakeholders, everybody wants to vote.
Yes. So our current model has a somewhat simplified way of thinking about aggregation. Right now, we can do sort of average preference across a group, maybe weighted averages with a bit of tweaking. This is incomplete in many settings because average is not necessarily the right way to think about aggregation. This is especially, I think, tricky in things like fairness settings, where we think that it's clear that many of the stakeholders may have extremely different opinions of sort of what the metric should be. And so there's a meta problem of choosing or thinking about how one can sort of better aggregate that we haven't solved yet. We've started to think about it in a careful way, and I can't say that we have any clear results. I think we've been taking some inspiration from work in sort of the economics world, where they think about social good and elicitation as well. The specific methods and settings are somewhat different, but the problems, at least a 10,000-foot view, are similar. And so they have methods in different settings. Often there, you still also need to decide what aggregation means, but then under the aggregation strategy, you can come up with sort of good combination methods. But that's sort of the first direction that we've been considering. Still an open problem, though.
It's great because every question kind of leads me into the next, and I swear we didn't agree to the questions beforehand. We definitely didn't. So this kind of is my question as a combination of the questions above, because we talk about sample complexity and queries to reach a good estimate of the parameters, and also we've been talking about multiple stakeholder settings. So combining the two, I wonder if you could, in a multi-stakeholder setting, estimate the degree of confidence in a metric. Use the degree of confidence in a metric as opposed to a pairwise ranking. Mm-hmm. And then I have a question about economists and that. And degree of confidence.
Yeah, so we dabbled a little bit in other kinds of query strategies to see sort of what effect they will have. We have sort of initial work both on there's an applied side to this, which is sort of how good are people and given various kinds of query responses. Confidence is tricky. We've played with auction queries a bit, which is a way to get at confidence, because it's sort of how much would you pay to get this kind of result versus other result, and maybe that gets you something closer to a confidence value. Algorithmically, I should say that at least our current analysis for these kinds of methods suggests it's a constant effect. Mm-hmm. So the sort of, you still need to pay some complexity to roughly scale to the number of parameters that you are interested in eliciting. So how complex your sort of metric function class is plays a key role. Right. But the constants can get better if you have better queries. That's what so far in our methods. This is a very likely, it's possible that this is, we're not clever enough to come up with better query elicitation methods, and maybe the clever methods can take advantage and actually reduce the rates. But on the sort of on the theoretical or algorithmic side, our results suggest that it can help, but it will help in sort of constant factors, if you like.
Interesting. Yeah, I was
in practice that could be big, by the way. So it's not meant to be dismissive. It can actually make a big difference.
Right, I was thinking about this because, and it's funny you mentioned economists in the previous answer, because we have colleagues of ours that are economists at Microsoft, and particularly been thinking about quadratic voting, which I actually had to go on Wikipedia and pull out the definition, which is a collective decision-making procedure which involves the individual allocating votes to express the degree of their preferences rather than just a direction. I don't know if anybody has proved. I know I'm loosely familiar because we've been talking about it, but I don't know if anybody has shown any proof as to what kind of rate of convergence towards good is. But is this kind of one of the things you consider? I think this is pretty popular in economics.
Yeah, we've thought about it a bit. We haven't actually tried it, so
cool.
Very tentative. I think we've thought the most about auctions because they seemed reasonably natural in terms of, again, trying to get at truthful preferences. But yeah, I think other strategies sound like definitely worth checking out. So
great. And I had one more question, but I will hold it for when we get to talk to each other because we are out of time. And in any case, thank you so much for the amazing talk and for responding to answering all these questions, both in the chat and now with me in the Q&A. For people, the recording, who want to rewatch it maybe, the recording is going to be available I guess soonish, next few weeks. Thank you again so much for
Thank you.
presenting.
It's a pleasure.